And we're back. So again, section 6.7, 6.8, and 6.9 are all places where, it doesn't really fit in anywhere else. Section 6.7 is graphing by hand, and we're going to talk about end behavior as well. Section 6.8 is transforming, right? Remember all those transformations, moving it left, right, up, down, all of those rules to follow. And then section 6.9 is, that regression stuff that we do in our calculator where we go list 1, list 2, we go through that process. Yeah, that's section 6.9. So a lot of things that we have base knowledge of, we just got to kind of dust off the cobwebs a little bit. So polynomial functions are classified by their degree, right? Classified by their degree. We've kind of talked about this at the beginning of the year. But polynomials in specific are classified by their degree, whether they're linear, quadratic, cubic, quartic, or quintic, 1, 2, 3, 4, or 5th degree. Okay? Each of those functions, based on their degree, you can kind of group them together and they all have similar characteristics. So I'm going to ask you to kind of just vaguely sketch those 5 graphs on your paper. So that because I want to see if you can define some patterns. I want to see if you can see the pattern within the graph. So we got linear function is degree 1, quadratic function is degree 2, cubic is degree 3, quartic is degree 4, quintic is degree 5. Obviously, that's something you learn all the way back in Algebra 1. Actually, funny enough, I literally just taught that in Algebra 1, like the names of all the polynomials. Like that was Friday, and they all freaked out on me. They're like, do we really have to learn this? Yeah. But you know the names of these things and in relation to their degrees. But now we can get we can kind of make some rules. We can kind of generalize what we see and see if there's any patterns. Does anybody see any patterns in relation to the number of degree and the look of the graph? Anybody see any patterns?
The odd ones start on the opposite side of the x-axis.
Very good. The odd ones start on the opposite side of the x-axis. Like the linear function, the left side goes down, the right side goes up. Cubic, the left side goes down, the right side goes up. Quintic, the left side goes down, the right side goes up. I'm glad she worded it the way that she did, because that doesn't necessarily always have to happen where the left side goes down, the right side goes up. But they must always start on opposite sides. That is true. The left side could go up, but then the right side must go down. So what does that imply about the even ones? What does that imply about the even ones? They start or end in the same direction. Whether they both go up or they could both go down as well. Yeah, good. What else do we see?
Like 4 different things. I don't know.
What do you mean?
Like for degree 4, there's 4 different lines. Like if you were to put points at the 3 different places.
I see. It goes, it decreases, increases, decreases, increases.
Yeah, same for 3 and.
Right, and same for all of them, right? Look at 5. It increases, decreases, increases, decreases, increases. So there's really 5 different places. So what does that mean? There's 4 actual whats. What are there 4 of then? Peaks or valleys, isn't there? We'll learn a little bit more technical name at the end of this section, maximums and minimums, local maximums, local minimums. Okay, 1, 2, 3, 4. So if there's 4 in degree 5, how many are there in degree 4? 3. How many in degree 3? 2. How many in degree 1 or 2? 1. How many in degree 1? 0. So there's always n minus 1, what we'll call turning points. Local maximums or local minimums. In calculus, we call those extrema, extreme values. What else? How many zeros do you see? How many zeros do you see? How many zeros do you see in degree 5? 5. How many in 4? 4. How many in 3? 3. How many in 2? It looks like 1, but it's really actually 2 because it bounces. Right? How many in 1? 1. So the number of zeros corresponds to the degree. That's that fundamental theorem of algebra that we learned. But we have to include multiplicities. That's why the quadratic almost looks like it breaks that rule. So we know a lot based on the degree. Like that's what I'm trying to instill in my Algebra 1 students. That right now we're just identifying what the degree is. You don't actually get to understand how the degree affects the shape of the graph until you get to this point in Algebra 2. Okay? Now, we talked about it going down on the left, up on the right, whatever. But that's called end behavior. Okay? That is called end behavior. We're going to learn a special notation to define end behavior. For example, end behavior is description of the values of the function as x approaches negative infinity or as x approaches positive infinity. All that basically means is I'm going to look at what's happening on the left side, and then I'm going to look at what's happening on the right side. As x approaches negative infinity means as x keeps getting smaller and smaller and smaller into the negative direction. As x approaches positive infinity, it means x gets bigger and bigger and bigger on the right side of the graph. Okay, so if I say as x approaches positive infinity, I'm saying on the right side of this graph, it does one thing. If I say as x approaches negative infinity, I'm saying on the left side of this graph, it does this thing. Okay, so here's the actual notation that we've got. And this is the second page, the top of the second page. You're going to fill these in. Now notice what we got as a setup here. I say leading coefficient a is greater than 0. What is another way to say a is greater than 0? A would be what then? Positive, right? If a is greater than 0, what I mean there is I say if a is positive, it's always got to it's always determined by the leading coefficient. The LC is positive. If the leading coefficient is positive, well, it's determined by the degree, whether it's odd or even, which we saw in the first slide there. An odd degree will go down on the left, leading coefficient positive odd degree will go down on the left, up on the right. Down on the left, up on the right. Doesn't matter whether it's a 3, a 5, a 7, a 9, it will always go down on the left, up on the right if it's a positive odd. So here's how we say that. As x approaches positive infinity, as x goes bigger and bigger and bigger and bigger, on the right side, the function p of x, the y values go up. Right? Up. That's what this notation is really saying. On the right, it goes up. Look at the bottom of that box. As x approaches negative infinity, as x gets smaller and smaller and smaller. So on the left, p of x, the y values go down. And then it kind of fills in from there for the rest of them as well. Notice that this is saying as x approaches negative infinity. So on the left, as x approaches negative infinity, as x gets smaller and smaller, the function goes up. Up on the left. As x approaches positive infinity, on the right, the function goes up. Notice that for even degree, they go the same direction, which is the pattern that we saw in the last slide, but they both go the same direction, they both go up. That's if the leading coefficient is positive. Positive. Positive odd, down on the left, up on the right. Positive even, up on the left, up on the right. I mean, you can kind of see what's going to happen on the second part of this diagram, or the second part of this table. It says as x, leading coefficient a is less than 0. So all I'm saying there is my leading coefficient is going to be negative. Does anybody still need this up top? Okay. So the leading coefficient is negative. When the leading coefficient is negative, well, think about it. If A is negative, what had happened? That's a vertical reflection, right? It's a vertical reflection. I'm changing all the y values, right? So all the bottoms go up top, which means if it looked like this for positive odd, it's going to look like this for negative odd. Left arm going up, right arm going down. So on the left side, it goes up. On the right side, it goes down. That's what that notation is saying. As x approaches negative infinity, p of x approaches positive infinity. As x keeps getting smaller and smaller, the function goes up. As x approaches positive infinity, on the right side, the function goes down. P of x goes to negative infinity. That's for negative odd, excuse me. For negative even, on the left side, it goes down, and on the right side, it goes down. Because we saw on the last slide that, yes, indeed, they both go the same direction, whether they both go up or they both go down. Are you guys ready to learn the end behavior dance? Too bad we're doing it anyway. Okay, everybody stretch out. Ugh, don't pull a muscle. Okay. It's not your shoulder. All right, here we go.
Oh, no.
Everybody do this. You can do one finger. Everybody do this.
One finger.
I just can't wait for it to turn around, nobody's me.
I'm the only one doing it.
I appreciate it.
Hi.
Positive even. Then do this. Negative even. Now go right arm up. It's important that you go right arm up. Positive odd. Negative odd.
It's like a weird disco game.
Yeah.
Say, do
I
it
know.
again. Just do it, but 2 times better.
Positive even, negative even. Positive odd, negative odd.
Need half of it.
Positive even, positive odd, negative odd. So it goes positive, negative, positive, negative. It's important that the right arm goes up right after the negative even, right?
They can't see this on the video.
I know, I'm really
Turn your
sorry.
webcam on.
That's okay.
Turn it on.
Positive, negative, positive, negative. I guarantee we're going to be at the quiz and you guys are going to be like, it's going to be group testing time and you guys are going to be like,
No, I'll just
Got
put my fingers like against the table, like just like posing with my fingers.
All right, so let's take a look here. Identify the leading coefficient, the degree, and then the end behavior. Okay, so the leading coefficient, the degree, and then we'll write the end behavior. All right, so what is my leading coefficient of this? What is my leading coefficient? -1, right? I don't care about the fact that it's a 1. I care about the fact that this is negative. What's my degree? 4. Which is I don't care about the fact that it's a 4. I care about the fact that it's even. So this is a negative even. Negative even. Positive, negative, even. Right down here. Negative, even. Both arms pointing down. So if I'm looking at the end behavior, I know that it's going to do this. But unfortunately, that's not the formal way to write end behavior. We have to write out the formal way of writing end behavior. So the end behavior is, I'll abbreviate it, EB. We say, on the left side, as x goes to negative infinity, the function Q of x in this case, Q of x. Q of x, well, on the left side it went down, goes to negative. And then we have to, so that's on the left side. We described the left side. Let's describe the right side. As x keeps getting more positive, well, it also goes down. Q of x continues downward as well. And that's how we write the end behavior. Now, you're going to find that this piece of the end behavior is the same every single time. Every single time, that piece of the end behavior is the same. Because that's the premise. That's like saying, okay, on the right side, blah. And on the left side, blah. Whatever you say there. You just have to describe what's happening on the left and the right side. Remember when we started polynomials and there was a section 6.1 where you had to like describe what was going on? You know, this is the more formal way to describe what's going on. Okay? The fact that these are both negative on the end basically means that they're both going downward on either side. Let's try that again. This is your guys' next one, right? Okay. Okay, so my leading coefficient is 2, which means it's a positive. My degree is 5, which means it's an odd. Okay, positive odd. Positive even, negative even, positive odd. Right arm up, left arm down. Right arm up, left arm down. So we say the end behavior is as x goes to the left, as x approaches negative infinity, p of x goes to, okay, on the left side, it's going downward on the left side, right? So it's going to go downward. It's going to go to negative infinity. On the right side, as x goes up, the function goes up. If you want to write a plus in front of the positive infinity, you can do that. But whatever, you don't need to. Let's do that one more time, shall we? I know. Okay, so the leading coefficient looks like it's a -4 in this last one, which means that that's a negative number. The degree looks like it's a 3, so that's an odd. Okay, negative odd. Positive even, positive odd, negative odd. Up on the left, down on the right. Up on the left, down on the right. Okay, so that means the end behavior looks like this. As x goes to the left, the function, looks like it's r of x this time. The pirate's favorite function, r of x. I don't know, I just made that up. The function, on the left, it goes up. Oh, sorry, r of x is equal to, but r of x approaches up. And then on the other side, as x goes to the right, to positive infinity, the function goes down. R of x goes to negative infinity. Okay, so that's how we formally write the end behavior as x approaches, Okay? Now, we've discussed the end behavior. We've discussed all of these things about the graph. Oh, sorry, we got to now flip it. Sorry, I thought we were going to graph next. Identify whether the function graph has odd or even degree and positive or negative leading coefficient. So we just kind of have to like match our dance to the graph. All right, is it this? Is it this? Is it this?
No.
Is it this?
Yes.
So it's a negative, so positive, positive, negative, odd. It's a negative odd. Because again, it goes positive, negative, right? Obviously, the ones that are going the same direction are the evens. The ones that are going different directions are the odds. All right? Okay, is it this?
Yeah.
Okay, so positive even. Okay, that's not too bad. No. Okay, so let's take a look at graphing this by hand. No graphing calculator. Now, you can cry uncle and use your graphing calculator on your homework if you really get stuck. But I want you to try to figure it out without your graphing calculator. All right. So here's what we have to do. I want to graph this function by first identifying the end behavior. What is the end behavior? Well, this is a positive odd, right? The positive odd. Now, did I specifically ask for the formal end behavior? No, I just said graph this thing. So I'm okay if you say, well, if this is a positive odd, up on the right, down on the left. Like you could do that and say, okay, I know it's going to go up on the right, down on the left. If you want to formally write it out, more power to you. But then we say, okay, the other most important pieces to this graph is the zeros of this function. Is that factorable? No, that's not factorable. So now I have to find the zeros. My next step after I've exhausted my flowchart would be to go to my calculator. Can I do that? No. Now is the time where I say, okay, my p-value is -6. My q-value is 1. How did I get that? My p-value is my constant term. My q-value is my leading coefficient. This is going back to section 6.6. And then I say, okay, well, my p over q values are then plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, right? Because I basically just want to take the factors of -6, which are 1, 2, 3, and 6, make them both positive and negative, and then divide them by 1, the factors of q. But in essence, that's the same thing. So now we have to be very lucky guessers. What do you want to choose? We got 8 options. -3. Let's try -3. I don't know if that's going to work, but let's try it. 1, 4, 1, -6. Oh, what I mean by that is I haven't done this ahead of time. So, what? No. Let me just double check. 1, -3, 1, -3, -2. Yeah, that works. Wow, I did on the first try. So that gives me an x is equal to -3 for one of the roots. And then I've got x squared plus x minus 2. And the nice thing is that factors. X plus 2, x minus 1. So x is equal to -2, x is equal to positive 1. Okay, now at that point, I can say, well, there, I know then that it crosses at -3. It crosses at -3. It crosses at -2. And it crosses at positive 1. And I also know that it goes down on the left, up on the right. I just have to figure out what's happening in between there. So all I do is I make myself a little table of values. I say, okay, if I want to figure out what's going on in between, let's pick a number between -2 and -3, say -2.5. And let's pick a number, an easy number between -2 and positive 1. Let's pick 0. That's an easy number to compute. So when we run -2.5 through, let's see what we get. Well, you could use red calculators. No graphing calculators. So -2.5 cubed plus 4 times -2.5 squared plus -2.5 minus 6. Looks like it's a 0.875. But it's positive, so it goes up just barely like that. And then if I plug in 0, it's just going to give me my y-intercept, which is -6 out here on the end. 0, -6. So we'll just kind of put it right in between there. So what was the process? Figure out your end behavior. Figure out your end behavior. Run your P's and your Q's. Get the zeros, then make a table. Now there is one more piece to this that I did not get through. The turning points, the local maximums or minimums. Just kind of save those ones. I'll do that right at the beginning of class tomorrow. It's really easy. I'll probably be posting a video on it really quickly. It probably will take like a 2-minute little snippet for you guys to do. If you want to check that out, I'll post it on Canvas as well. Yeah, I think there are like a couple problems on your homework, so you can kind of save those. If you want to just do them at the beginning of class tomorrow, it's really easy. You just got to know where to push in your calculator. You got to know how to do it in your calculator. Okay, so long everybody at home.
Donald.